MEG 224, Engineering Mechanics 2, Dynamics. Lecture 4, Kinetics of Particles. The Principle of Work and Energy, Part C. This can be found in Chapter 14 of Engineering Mechanics Dynamics by R.C. Hibler. Objective of this lecture. The objective of this lecture is to develop the concept of power and efficiency, to introduce the concept of a conservative force, and apply the theorem of conservation of energy to solve kinetic problems. Power and efficiency. Power. What is power? The term power provides a useful basis for choosing the type of motor or machine which is required to do a certain amount of work in a given time. So when you talk of power, you talk of amount of work and you talk of time. So for example, two pumps may be able to empty a reservoir if given enough time. However, the pump having the larger power will complete the job sooner. The power generated by a machine or engine that performs an amount of work du within the time interval dt is therefore P is equal to du dt. If the work du is expressed as du is equal to F dr, then P is equal to du dt, and du is F dr. So, which is equal to F dr dt, and then F dr dt. And R is displacement, and dr dt is time rate of change of displacement. So, power will be F dot V. And that means this is a dot product, which is a scalar product. Hence, power is a scalar quantity. V represents the velocity of the particle, which is acted upon by the force F. The basic units of power used in SI and FPS units are the watts and horsepower, respectively. The units are defined as 1 watt is equal to 1 joules per second, which is equal to 1 Newton meter per second. For conversion between the two systems of units, 1 horsepower is equal to 746 watts. Efficiency. The mechanical efficiency of a machine is defined as the ratio of the output of useful power produced by a machine to the input of power supplied to the machine. Hence, efficiency is power output over power input. If energy supplied to the machine occurs during the same time interval at which it is drawn, then the efficiency may also be expressed in terms of the ratio of power. Since machine consists of a series of moving parts, frictional forces will always be developed within the machine. And as a result, extra energy or power is needed to overcome these forces. Consequently, power output will be less than power input. And so, efficiency of a machine is always less than 1. Conservative forces and potential energy. Conservative force. If the work of a force is independent of the path and depends only on the force's initial and final position on that path, then we can classify this force as conservative force. Examples of conservative forces are the weight of a particle and the force developed by a spring. The work done by the weight depends only on the vertical displacement of the weight, and the work done by a spring force depends only on the spring's elongation or compression. In contrast to a conservative force, consider the force of friction exerted on a sliding object by a fixed surface. The work done by the frictional force depends on the path. The longer the path, the greater the work. Consequently, frictional forces are non-conservative force. The work is dissipated from the body in the form of heat, energy. Energy is defined as the capacity for doing work. For example, if a particle is originally at rest, then the principle of work and energy states that summation U1 to 2 is equal to T2, because that the particle is originally at rest. Therefore, T1 is 0. You know, T is kinetic energy, so which is half mv square. And then when the object is at rest, V is 0. So the initial term or the initial kinetic energy is absent. So in other words, the kinetic energy is equal to the work that must be done on the particle to bring it from a state of rest to a speed V. Thus, the kinetic energy is a measure of the particle's capacity to do work, which is associated with the motion of the particle. So we know here that this T2, this is equal to half mv2 square. So when energy comes from the position of the particle, measured from a fixed datum of reference plane, it is called potential energy because it is due to the position. Thus, potential energy is a measure of the amount of work a conservative force will do when it comes, when it moves from a given position to the datum. In mechanics, the potential energy created by gravity, weight, or an elastic spring is important. Gravitational potential energy. If a particle is located a distance y above an arbitrarily selected datum as shown in the figure, the particle's weight, W, has positive potential energy, Vg, since W has the capacity of doing positive work when it's moved back to the position of datum down here. And then likewise, if the particle is located below the datum line, Vg is negative since the weight does negative work when the particle is moved back up to datum line. At that datum, Vg is 0. This is the datum. Vg is 0. In general, if y is positive upward, the gravitational potential energy of the particle of weight W is Vg is Wy. Elastic potential energy. When an elastic spring is elongated or compressed a distance s from its unstretched position, elastic potential energy VE can be stored in the spring. Here, this is the original position. Here it is stretched. Here it is compressed. When it is stretched or when it is compressed, elastic energy can be stored in it. This energy is V is equal to half Ks squared. So if VE is here, VE is always positive in the deformed position. The force of the spring has the capacity or potential for always doing positive work on the particle when the spring is returned to its unstretched position. Conservation of energy. When a particle is acted upon by a system of both conservative and non-conservative forces, the position or the portion of the work done by the conservative force can be written in terms of the difference between their potential energies. Work from 1 to 2 conservative is V1 minus V2. As a result, the principle of work and energy can be written as T1 plus V1 plus this, that is the work done by non-conservative forces, is equal to T2 plus V2. So here, the work done by non-conservative forces represents the work of non-conservative forces acting on the particle. So if only conservative forces do work then we have T1, so this one becomes 0. This guy strikes out. So T1, V1, T1 plus V1 is equal to T2 plus V2. This equation is referred to as the conservation of mechanical energy, or simply conservation of energy. It states that during the motion, the sum of particles' kinetic and potential energies remain constant. For this to occur, Ke must be transformed into Pe and vice versa. For example, if a ball of weight W is dropped from height H above the ground, as this the H, this is the ball, and is dropped to the ground, then the potential energy of the ball is maximum before it is dropped here, at which time its kinetic energy is 0. Because the velocity is 0, kinetic energy will be 0. So the total mechanical energy of the ball is in its position. So it's only potential energy that it possesses. So E will now be T1 plus V1 is equal to 0, because T1 is 0. Kinetic energy at that point 1 or is 0, which is WH. V1, which is the potential energy, and W is the weight, which is mg. So this guy now is mgh. So this guy, this is mgh. So when the ball falls a distance h/2, its speed can be determined by using v square is equal to v naught square plus 2ac into y minus y naught. Here, AC is constant acceleration, which is g, which yields that v is equal to root gh after, because these two cancels out these two. Then what you have left is root gh. The energy of the ball at the middle height position is therefore E is equal to T2 plus V2. T2, that's the kinetic energy, is half. This guy, W, is mg. So from the mg, so this is mg. So G can cancel out. Then you have M. Half M V square. So since this is V square, we have already gotten this as V square here. So, and it's brought here. So V is here. V is here. This is V. This is V. So Of course, the square will cancel out the square root, plus the potential energy V, this is mgh, and the h here now is h/2, which is half. So which is still wh, and it's still the same as our first expression. This is at the middle point, energy at the middle point. At the beginning, this is the energy. At the midpoint, this is the energy. So just before the ball strikes the ground, its potential energy is 0, and the speed is still z. V is equal to 2gh. No. So here again, the total energy of the ball is E is equal to T3 plus V3 here, half W/G root 2gh square plus 0. Note that when the ball comes in contact with the ground, it deforms somewhat, and provided the ground is hard enough, the ball will rebound off the surface, reaching a new height, h prime, which will be less than the height h from which it was first released. Neglecting air friction, the difference in height accounts for an energy loss. So the energy loss, E, is equal to W into h minus h prime, which occurs during the collision. Portions of this loss produce noise, localize the formation of the ball and the ground, and then heat. System of particles. If a system of particles is subjected only to conservative forces, then an equation similar to the one that I've been developing can be written for the particles. Applying the idea of the preceding discussions, we just sum all the terms together. So summation T1 plus summation U1 to 2 is equal to summation T2, becomes summation T1 equal plus summation V1 equals summation T2 plus summation V2. Here, the sum of the system's initial kinetic energy and potential energies is equal to the sum of the system's final kinetic energy and potential energy. In other words, summation T plus summation V is equal to constant. End of part C. Thank you. Do not forget to like, to subscribe, to share. Please press the notification bell for new videos. If you are one of my university undergraduate students, please do not forget to subscribe with your real name. Thank you.